Persistent memory is a recent technology that offers a midpoint performance between RAM and traditional SSDs and HDD disks, combined with data persistency guarantees. Persistent memory is not intended to replace either RAM or SSDs HDDs, but rather to act as a middle tier between those, opening the opportunity for high-performance application programmers to explore novel designs and applications. Persistent memory provides two different abstractions to the programmer: either direct access to the memory and hence acting like regular memory, or a block device abstraction and hence acting like a regular disk. Without crashes, persistent memory offers the best of both worlds: speed and persistency. Unfortunately, persistent memory benefits come at the cost of potential inconsistencies when the application or the machine crashes. This means that programmers need to carefully build or rewrite their existing applications to take into consideration the characteristics of the hardware and explicitly issue flush and fence instructions, among others. This requires substantial technical knowledge, even for experienced programmers, because this is a new technology, and therefore it's an error-prone process that can lead to bugs. In some cases, such programming bugs can lead to data loss due, for instance, the absence of a single instruction, while in other cases, excessively defensive programmer can forfeit the performance benefits of persistent memory. There are several state-of-the-art approaches that attempt to detect those bugs in existing applications, but they are either very slow, or they require programmers to manually annotate their code, which is in itself also error-prone. Other approaches do not scale well to very large applications, and even others have a combination of these limitations. In this exploratory project, we propose a set of tools that can detect programming bugs in both applications that use persistent memory through this memory abstraction or through a block device interface. The key idea, the main intuition of our approach, unlike the state-of-the-art, is to rely on application-specific modules that capture usage patterns that might lead to incorrect behavior. The existence of these patterns allows us to analyze applications in a fully automated and efficient way by searching for the occurrence of these patterns, and when they appear we can tell with certainty there is a bug, and we can do this in an automated way as well. As some examples, we have developed MUMAC, which is a tool for evaluating crash consistency on the persistent memory as a regular memory model abstraction. We also have developed a KillsBench, which is a fault injection benchmark for persistent memory as a disk model. We also have developed BDUS, which is a framework for implementing block devices in user space. And we also have developed CrashMonkey PM, which is a crash consistency testing framework for persistent memory file systems. Some of these systems we have already published, while for the others we are in the process of preparing their submission to conferences. Moreover, because this is an emerging area, we also want to contribute to this community by releasing all the code that we are going to develop as open source in the near future.